Picture this: you're sitting by a campfire, feeling the warmth of the flames lick at your skin. But something strange happens when you hold your hand above the fire. The air just above the flames feels scorching hot, far hotter than the fire itself. Now imagine that same bizarre twist of nature, but on a scale so massive it defies logic. Welcome to the greatest solar mystery of our time. The surface of our sun burns at a blistering 5,500 degrees Celsius. Yet just above it, the sun's wispy outer atmosphere, the corona, rages at a mind bending 1 to 3 million degrees. That's like standing next to a roaring bonfire only to discover the smoke above it is hundreds of times hotter than the flames. For over a century, this cosmic contradiction has baffled the brightest minds in science. How can the sun's atmosphere be hotter than its surface? What invisible forces are cooking the corona to unimaginable temperatures while the surface stays relatively cool? Strap in, because today we're diving deep into one of space's most perplexing puzzles, a mystery that holds the key to understanding everything from solar storms to the very nature of stars across the universe. And by the end of this journey, you'll see our familiar sun in a completely new light. To truly grasp this solar enigma, let's first peel back the layers of our star. Think of the sun like an onion, with each concentric shell revealing a different fiery personality. At the very heart lies the core, nature's ultimate nuclear furnace, where temperatures soar to an astonishing 15 million degrees Celsius. Here, hydrogen atoms fuse into helium, releasing the energy that powers our entire solar system. Moving outward, we reach the radiative zone, where this energy bounces around like a cosmic pinball for thousands of years before emerging into the convective zone. Picture this layer as a bubbling pot of plasma, with giant cells of superheated gas rising and falling like lava in a slow-motion lamp. Now we arrive at the sun's visible surface, the photosphere, the layer we typically think of as the sun's face. Surprisingly, this is actually one of the cooler regions, simmering at around 5,500 degrees Celsius. Above it lies the chromosphere, a thin reddish layer that's slightly hotter, reaching up to 20,000 degrees. But here's where things get truly bizarre. Beyond these layers stretches the corona, the sun's wispy outer atmosphere that defies all expectations. While you'd logically expect temperatures to decrease as you move away from the core, the corona instead erupts into an inferno between 1 and 3 million degrees, hundreds of times hotter than the surface below it. This temperature inversion is as perplexing as finding frost at the base of a volcano and scorching heat at its summit. The photosphere should logically be the hottest visible layer, yet the tenuous corona above it burns with unimaginable intensity. What could possibly cause such a dramatic reversal in the expected temperature pattern? That's the million-degree question we'll explore next as we trace how scientists first stumbled upon this solar paradox. Now, let's step back in time to uncover how this cosmic puzzle first caught the attention of scientists. The story begins in the late 19th century, when astronomers noticed something strange during solar eclipses. As the moon blocked the sun's bright face, they observed a faint, pearly glow stretching far into space, the corona. Early spectrographs, which break light into its component colors, revealed something even more shocking. The corona's spectral lines didn't match any known elements on Earth at the time. This led to the discovery of a new element, or so they thought. Scientists named it coronium, only to later realize it wasn't an element at all but superheated iron stripped of most of its electrons, a clue to the corona's extreme temperatures. Fast forward to the mid-20th century, when a young physicist named Eugene Parker proposed a revolutionary idea. He suggested that the sun's atmosphere wasn't static but constantly flowing outward, a phenomenon he called the solar wind. At first, many dismissed his theory, but spacecraft like NASA Mariner 2 later proved him right. Parker's work laid the foundation for understanding how the corona's energy might escape into space. Then came the game changers, space telescopes and probes designed to study the sun up close. The Solar and Heliospheric Observatory, or SOHO, launched in 1995, gave us unprecedented views of the corona's structure and dynamics. But the real breakthrough arrived with the Parker Solar Probe, named in honor of Eugene Parker himself. This daring spacecraft flew closer to the sun than any human-made object before, braving brutal heat to measure magnetic fields, particles, and waves in the corona itself. Each of these milestones peeled back another layer of the mystery, showing us that the corona's heat isn't just a fluke, it's a fundamental piece of how our sun works. And with every new observation, we get closer to solving this sizzling enigma. Here's how the corona's temperature paradox defies common sense. Picture standing near a campfire. The flames are hot, but the air just above them is even hotter, so hot it could melt steel. That's essentially what's happening with the sun, but on a mind-bending scale. The sun's visible surface, called the photosphere, sits at around 5,500 degrees Celsius. That's already scorching hot enough to vaporize rocks instantly. But just above it, the corona blazes at 1 to 3 million degrees. Think about that for a second. If you moved away from a heat source on Earth, like stepping back from a stove, the air gets cooler. Not so with the sun. The farther you go from its surface, the hotter it gets. It's like walking away from a bonfire and suddenly feeling your skin blister from invisible, superheated air. Scientists call this the coronal heating problem, and it's one of the biggest head-scratchers in solar physics. Why does this matter? Because understanding this paradox isn't just about solving a cosmic riddle, it's key to predicting solar storms that can knock out satellites, disrupt power grids, and even endanger astronauts. The corona's heat fuels the solar wind, that stream of charged particles constantly washing over Earth. So cracking this mystery isn't just science for science's sake. It's about protecting our tech-dependent world. Next, we'll dive into the invisible force shaping this inferno, the sun's magnetic field, and how its twists and snaps might hold the answer. Now, let's unravel the invisible powerhouse behind this solar enigma, the sun's magnetic field. Unlike Earth's relatively steady magnetic field, which acts like a giant bar magnet shielding us from cosmic radiation, the sun's magnetism is a chaotic, ever-shifting force. It's born from the churning plasma deep within the sun, where electrically charged particles swirl and twist, generating magnetic fields like a cosmic dynamo. Picture a pot of boiling water, but instead of water, it's superheated gas or plasma bubbling violently. As these charged particles move, they drag magnetic field lines along with them, stretching and tangling them like spaghetti in a whirlpool. This constant motion creates a web of magnetic energy that snakes through the sun's atmosphere all the way up to the corona. Here's where things get fascinating. While Earth's magnetic field is strong enough to guide compass needles, the sun's is so intense it can shape entire loops of glowing plasma arcs large enough to swallow our planet whole. These magnetic loops aren't just spectacular to watch. They're the likely culprits behind the corona's extreme heat. When these fields snap and reconnect, they release explosive energy, like rubber bands breaking after being stretched too far. Understanding this magnetic chaos isn't just about solving a solar puzzle. It's a blueprint for how energy travels from the sun's interior to its outer layers, and ultimately how it supercharges the corona. Next, we'll see how these magnetic explosions, called reconnections, might be the missing piece of the heating mystery. Now, let's zoom in on one of the most dramatic events in solar physics, magnetic reconnection. Imagine those twisted magnetic field lines we just talked about, tangled like a bundle of wires. When they get stretched too far, they don't just sit there, they snap. And when they do, it's like a cosmic short circuit, releasing a burst of energy that can heat the surrounding plasma to millions of degrees in seconds. This isn't just theory. Spacecraft like NASA's magnetospheric multiscale mission have caught magnetic reconnection in action, watching as fields break apart and reform. flinging particles away at nearly the speed of light. On the Sun, these explosions are even more extreme. Picture a rubber band stretched until it snaps, except here, the rubber band is a magnetic loop thousands of miles long, and the snap unleashes enough energy to power cities for years. What's wild is how common this is. The Sun's corona isn't just heated by the occasional big flare, it's constantly buzzing with tiny reconnections like popcorn popping in a pan. Each one might be small, but together they could be the steady heat source keeping the corona sizzling. Recent high-resolution images from the Solar Dynamics Observatory show these events happening all over the Sun, especially where magnetic fields are most tangled. But here's the twist: reconnection doesn't just heat the plasma, it also slingshots it outward, helping to fuel the solar wind. So solving this puzzle doesn't just explain the corona's heat, it ties into how the Sun shapes the entire solar system. Next, we'll explore another piece of the mystery: waves of energy rippling through the Sun's atmosphere like invisible tsunamis. Now, let's turn our attention to another fascinating piece of the puzzle: Alfvén waves. These are not your ordinary waves. Picture them as ripples racing along the Sun's magnetic field lines, like vibrations traveling down a guitar string. But instead of sound, they carry massive amounts of energy straight into the corona. Named after the Nobel Prize-winning scientist Hans Alfvén, these waves form when the Sun's magnetic field gets jostled by the constant churning of plasma beneath it. As the waves travel upward, they don't just fade away, they grow stronger, dumping their energy into the corona like a delivery truck unloading heat. Here's where it gets even more exciting. NASA Parker Solar Probe, the spacecraft that's flying closer to the Sun than any mission before, has actually detected these waves in action. As it skimmed through the corona, its instruments picked up sudden, sharp flips in the magnetic field, nicknamed switchbacks, which scientists believe are tied to Alfvén waves. These switchbacks act like speed bumps, transferring energy from the waves into the surrounding plasma, heating it up in the process. What's remarkable is how efficient this process could be. Unlike explosive flares or reconnection events, Alfvén waves provide a steady, rhythmic way to pump heat into the corona. Think of it as turning up a thermostat slowly instead of blasting a furnace. Some researchers argue these waves might be the missing link, explaining why the corona stays so hot even when the Sun isn't erupting with big flares. But the story doesn't end here. Up next, we'll dive into another contender in the coronal heating mystery: tiny but mighty explosions called nanoflares. Could these miniature bursts be the final piece of the puzzle? Stay tuned. Now, let's zoom in on something much smaller but no less powerful: nanoflares. Imagine billions of tiny explosions happening all across the Sun's surface, each one too small to notice on its own, but together they could be the secret behind the corona's extreme heat. These nanoflares are like miniature versions of the massive solar flares we often hear about, but instead of one big burst, they're a constant crackle of energy. Scientists first proposed this idea decades ago, suggesting that even if each nanoflare is weak, their sheer numbers could add up to heat the corona significantly. Recent observations from high-resolution telescopes like NASA's Solar Dynamics Observatory have given us glimpses of these tiny bursts. Some regions of the corona show brightening and fading in ways that match what we'd expect from nanoflares. But here's where the debate kicks in. While some researchers argue these events are everywhere, others think they might not be frequent enough to explain the corona's temperature entirely. One of the biggest challenges is detecting them. Nanoflares are so small and quick that even our best instruments struggle to catch them in action. It's like trying to spot fireflies in a thunderstorm, possible but far from easy. So, are nanoflares the answer? They're definitely a strong contender, but the mystery isn't solved yet. Next, we'll look at another piece of the puzzle: how the chaotic swirl of plasma itself might be stirring up the heat in ways we're just beginning to understand. Now, let's stir things up literally. The Sun's corona isn't just heated by explosive events like nanoflares. there's another player in this cosmic kitchen: plasma turbulence. Picture the sun's outer layers as a pot of boiling water, but instead of water, it's superheated plasma, a soup of charged particles swirling in chaos. This turbulence isn't just random noise. When plasma moves unpredictably, it creates tiny whirlpools and eddies that collide and twist, much like stirring a cup of coffee. Those collisions don't just fizzle out, they convert motion into heat, dumping energy into the corona. Scientists call this dissipation, where the plasma's wild motions gradually settle down, leaving behind warmth. Here's where it gets fascinating. The sun's magnetic fields don't just sit there, they get tangled up in this turbulent dance, stretching and snapping like rubber bands. That adds even more energy to the mix, turning the corona into a giant heat trap. Some researchers think this could be the missing piece, explaining why certain parts of the corona stay scorching hot, even when there aren't obvious flares or explosions. But turbulence is tricky to study. Unlike nanoflares, you can't spot it with a telescope. It's more like trying to track the ripples in a stormy ocean from space. Supercomputer simulations help, modeling how these chaotic flows might transfer energy. The results, they hint that turbulence could be working alongside other heating mechanisms, like a backup generator keeping the lights on. So, is turbulence the sole answer? Probably not, but it's another clue in this solar whodunit. Up next, we'll examine how the sun's glowing magnetic arches, called coronal loops, might be funneling heat into the corona like invisible highways. Now, let's turn our attention to one of the most breathtaking sights in solar science: coronal loops. These towering arcs of glowing plasma aren't just beautiful, they're like the sun's hidden heating system, stretching tens of thousands of miles above the surface. Imagine giant, glowing bridges made of magnetic fields, channeling energy into the corona with every twist and pulse. Here's how they work. Coronal loops form when the sun's magnetic field lines get stretched and anchored to the surface, trapping superheated plasma along their curves. But these loops aren't static, they constantly vibrate and sway, almost like guitar strings being plucked. Every oscillation sends waves of energy racing upward, dumping heat into the corona. Scientists call this wave heating, and it's one of the leading theories for why the corona stays so blisteringly hot. But there's more. These loops don't just sit quietly, they interact. When two loops cross or reconnect, they can release bursts of energy, much like tangled ropes snapping apart. Satellite images from missions like the Solar Dynamics Observatory show this drama in stunning ultraviolet light, revealing loops brightening suddenly as they clash or merge. It's a vivid reminder that the corona isn't just heated by one thing. It's a symphony of mechanisms working together. What's really intriguing is how these loops vary. Some are steady and long-lasting, while others flicker and fade quickly. That inconsistency hints at something deeper. Maybe different types of loops play different roles in heating the corona. For example, smaller, more dynamic loops might contribute to sudden temperature spikes, while larger, stable ones could provide a steady simmer. Of course, coronal loops aren't the full answer either. But they're another critical piece of the puzzle, showing how the sun's magnetic artistry turns the corona into a furnace. Next up, we'll explore how all this heat doesn't just stay put. It fuels the solar wind, a stream of particles racing across the solar system. Now, here's something fascinating. The corona's heat doesn't just sit there. It actually powers one of the sun's most far-reaching phenomena, the solar wind. Picture this, a constant stream of charged particles racing outward from the sun at speeds of up to 1,000,000 miles per hour. But how does this relentless wind connect to the corona's scorching temperatures? It all comes down to energy. The same processes that heat the corona: magnetic reconnection, Alfvén waves, and those dynamic coronal loops also give the solar wind its kick. As the corona gets superheated, the intense energy allows particles to break free from the sun's gravity, accelerating them into space. Think of it like a boiling kettle. The hotter the steam, the more forceful the burst. But why does this matter? Because the solar wind isn't just a cosmic curiosity. It's a key player in space weather. When those high-speed particles collide with Earth's magnetic field, they can create dazzling auroras, but they can also disrupt satellites, knock out power grids, and even pose risks to astronauts. Understanding how the corona heats up isn't just about solving a solar mystery. It's about predicting these space weather events before they happen. Here's the kicker. The better we grasp the corona's heating mechanisms, the more accurately we can forecast the solar wind's behavior. Missions like the Parker Solar Probe are giving us unprecedented data, showing how waves and magnetic fields near the sun's surface funnel energy into the wind. It's like finally seeing the engine behind the storm. So while the corona's heat might seem like a distant puzzle, its implications are anything but. From protecting our technology to unlocking the sun's secrets, this is science with real stakes. And speaking of stakes, next up we'll look at the chromosphere, the sun's middle layer where things get even more intriguing. Now let's zoom in on the sun's chromosphere, the often overlooked middle layer that plays a crucial role in this temperature puzzle. Sandwiched between the relatively cool photosphere and the blazing corona, the chromosphere is like a turbulent highway where energy gets transferred upward. But how does this thin, reddish layer act as a bridge between two extremes? One of the chromosphere's most striking features is its spicules, jet-like eruptions that shoot up at staggering speeds, some reaching tens of thousands of miles per hour. These dynamic spikes are like nature's energy elevators, ferrying heat and plasma toward the corona. Scientists believe spicules could be a key piece of the heating mystery, delivering bursts of energy that help maintain the corona's extreme temperatures. Imagine tiny geysers constantly pumping heat into the upper atmosphere. Each one might seem insignificant, but together they could pack a serious punch. But here's the twist: not all spicules are created equal. Some are short-lived while others last longer, and their energy contribution is still hotly debated. Recent observations suggest they might work in tandem with other mechanisms, like magnetic reconnection or Alfvén waves, to keep the corona sizzling. It's as if the chromosphere is a bustling factory floor, with multiple assembly lines feeding energy upward. What makes this layer even more fascinating is its transparency. Unlike the photosphere, which blocks our view of the sun's interior, the chromosphere lets certain wavelengths of light pass through, giving us a unique window into the sun's inner workings. Tools like the Solar Dynamics Observatory have captured stunning images of spicules in action, revealing their intricate dance. Yet, despite these advances, the chromosphere remains full of open questions. So, while the corona steals the spotlight with its scorching heat, don't underestimate the chromosphere's behind-the-scenes role. It's not just a passive middleman, it's an active player in the sun's energy game. And as we piece together how spicules and other processes contribute, we get closer to solving one of the sun's most enduring mysteries. Up next, we'll dive into the competing theories about how all this energy actually reaches the corona. Because when it comes to the sun, every layer has a story to tell. Now, shifting our focus to the heart of the debate, let's explore the two leading theories trying to crack the coronal heating mystery: wave heating versus magnetic reconnection. Both ideas have passionate supporters and compelling evidence, but which one holds up under scrutiny? First up, wave heating. Picture the sun's magnetic field lines as giant guitar strings. When they're plucked by turbulent plasma motions, they produce vibrations called Alfvén waves. These waves travel upward, carrying energy from the sun's surface into the corona, where they dissipate as heat. It's like ocean waves crashing onto a shore, releasing their energy in a burst of warmth. The Parker Solar Probe gave this theory a boost when it detected these waves in action, showing they're strong enough to contribute significantly to coronal heating. But here's the catch: while Alfvén waves are undeniably present, some calculations suggest they might not deliver enough energy to explain the corona's extreme temperatures alone. On the other side, we have magnetic reconnection. Imagine two rubber bands twisted together until they snap, releasing a burst of energy. That's essentially what happens when the sun's tangled magnetic field lines break and reconnect, converting magnetic energy into heat. This process is spectacularly visible during solar flares, but scientists argue smaller, frequent reconnections, nanoflares, could be quietly heating the corona all the time. High-resolution images from the Solar Dynamics Observatory show countless tiny brightenings that might be these nanoflares at work, the strength of this theory. It neatly explains sudden temperature spikes and the corona's patchy heat distribution. Yet, critics point out that we haven't observed enough nanoflares to account for all the heat, leaving gaps in the puzzle. So, which theory wins? The truth might lie in a combination of both. Recent studies suggest Alfvén waves could prime the corona, creating conditions where magnetic reconnection becomes more efficient. Think of it like a campfire. Waves might be the kindling, while reconnection acts as the logs that sustain the blaze. Data from newer missions like the Solar Orbiter could help settle the debate by mapping the sun's magnetic field in unprecedented detail. What's clear is that neither theory has a monopoly on the answer. The sun, as always, refuses to make it simple. Up next, we'll see how cutting-edge technology, like the Parker Solar Probe's daring dives into the corona, is bringing us closer than ever to solving this sizzling mystery. Now, let's zoom in on the Parker Solar Probe, the daring spacecraft that's rewriting the rules of solar science. Flying closer to the sun than any mission before, it's peeled back the curtain on the corona's secrets with jaw-dropping discoveries. One of its biggest revelations, strange, zigzagging kinks in the sun's magnetic field, nicknamed switchbacks. Picture a highway suddenly twisting into sharp U-turns. That's what these magnetic waves do, snapping and reorganizing in ways we never expected. These switchbacks could be dumping massive energy into the corona, like invisible power lines short-circuiting and sparking heat, but that's not all. The probe also caught whispers of nanoflares, those tiny explosions we talked about earlier. Its instruments detected bursts of energy so small they'd been invisible from afar, yet frequent enough to collectively roast the corona. Think of it like popping popcorn. One kernel isn't hot enough to cook dinner, but a whole pan, that's a game changer. Perhaps most thrilling is how the probe measured the corona's chaotic particle speeds. Solar wind particles don't just drift away smoothly. They're catapulted at wild, uneven velocities, as if the corona is a giant particle accelerator. This turbulence hints that both Alfvén waves and magnetic reconnection might be teaming up, like a cosmic tag team heating the atmosphere. The Parker probe's data is still pouring in, but one thing's certain. Every scrape with the sun's fury brings us closer to solving the million-degree mystery. Next up, we'll see how another high-tech eye in the sky, the Solar Dynamics Observatory, is filling in more pieces of this scorching puzzle. Now, shifting our gaze from the daring close-ups of the Parker Solar Probe, let's turn to the Solar Dynamics Observatory, or SDO, a mission that's been our unwavering eye in the sky for over a decade. While Parker gets up close and personal, SDO gives us the big picture, stunning, high-resolution snapshots of the sun's drama in real time. Imagine watching a movie where every frame reveals intricate details of the corona's fiery ballet, and you'll get a sense of what SDO delivers. One of its most breathtaking contributions, capturing coronal loops in exquisite detail. These towering arches of superheated plasma, shaped by the sun's magnetic field, glow brilliantly in ultraviolet light. SDO's images show them twisting, stretching, and even snapping like overstretched rubber bands, releasing energy that heats the surrounding corona. It's like watching a cosmic lightning storm where every flash leaves behind a trail of scorching heat. But SDO doesn't just stop at pretty pictures. Its instruments track solar flares, those sudden, violent bursts of energy, with precision. By studying how flares erupt and interact with coronal loops, scientists have spotted clues that magnetic reconnection isn't just a rare event. It's happening constantly, like a never-ending game of magnetic dominoes. And when these dominoes fall, they dump energy into the corona, pushing its temperature into the millions of degrees. What makes SDO truly groundbreaking is its ability to monitor the sun around the clock. Unlike missions that take occasional snapshots, SDO streams data non-stop, giving researchers a front-row seat to the sun's ever-changing moods. This relentless surveillance has revealed patterns in solar activity, helping us predict how and when the corona might unleash its next fiery tantrum. So while Parker probes the sun's secrets from the inside, SDO paints the full portrait from afar, and together, they're bringing us closer than ever to cracking the corona's million-degree mystery. Up next, we'll dive into how supercomputers are simulating these solar fireworks, testing theories without ever leaving Earth. Now, let's step into the digital realm where supercomputers are unlocking the sun's secrets without ever leaving the lab. These powerful machines take the data from missions like Parker and SDO and bring it to life in stunning virtual simulations. Picture this: scientists feed equations into these computational giants, and out comes a dynamic, ever-changing model of the sun's magnetic fields, plasma flows, and energy bursts, all in breathtaking detail. One of the biggest challenges in understanding the corona's heat is that we can't recreate its extreme conditions on Earth, but supercomputers, they don't have that limitation. By crunching mind-boggling amounts of data, they simulate how tangled magnetic fields snap and reconnect, how Alfvén waves ripple through the plasma, and how countless nanoflares might collectively turn up the temperature. It's like having a virtual laboratory where you can tweak variables adjusting the strength of magnetic fields or the density of plasma, and instantly see how those changes affect the corona. These simulations have revealed something fascinating. The corona's heating isn't just one process but a symphony of mechanisms working together. Sometimes magnetic reconnection dominates, other times it's waves or turbulence, and often it's a mix of all three. Supercomputers let scientists test these scenarios side by side, comparing which theories match real observations best, and the visuals, they're nothing short of mesmerizing. Imagine swirling ribbons of magnetic energy, twisting and braiding like cosmic spaghetti, or waves surging through the corona like ocean tides. These aren't just pretty animations, they're precise mathematical predictions helping us visualize what's happening millions of miles away. What's truly groundbreaking is how these simulations bridge the gap between theory and reality. When Parker or SDO spot something unexpected, scientists can plug that data into their models and see if their virtual sun behaves the same way. It's a constant back and forth, refining our understanding one calculation at a time. So while telescopes and probes give us snapshots of the sun's behavior, supercomputers stitch those glimpses into a moving picture, one that's bringing us closer than ever to solving the corona's scorching mystery. Next, we'll explore why Earth-based telescopes struggle to study the corona and how space missions are filling those gaps. Now, let's talk about why studying the sun's corona from Earth isn't as straightforward as you might think. Even with the most advanced ground-based telescopes, scientists face some serious hurdles. The biggest challenge, our own atmosphere. The air around us might seem clear, but it's actually a swirling mess of moisture, dust, and turbulence, all of which distort the light coming from the sun. Imagine trying to look at a crisp, detailed image through a glass of rippling water. That's what astronomers deal with every day, but it's not just blurriness. Earth's atmosphere also blocks certain types of light, like extreme ultraviolet and X-rays, which are crucial for studying the corona's superheated plasma. It's like trying to solve a puzzle with half the pieces missing. And then there's daylight. Most telescopes can't even observe the corona unless there's a total solar eclipse, when the moon briefly blocks the sun's blinding surface. That's a tiny window of opportunity, and it doesn't happen often. This is where space telescopes come in. Free from atmospheric interference, instruments like NAS, a Solar Dynamics Observatory, or the European Space Agency's Solar Orbiter, can observe the corona 24/7 in wavelengths of light that never reach the ground. They capture razor-sharp details of magnetic loops, solar flares, and plasma eruptions without any distortion. Plus, they can monitor the sun continuously, tracking changes over time, something ground-based telescopes simply can't do reliably. There's another advantage to going to space: stability. On Earth, even the slightest vibration from wind, traffic, or even footsteps can jiggle a telescope enough to ruin its focus. In the quiet of space, instruments stay perfectly steady, delivering crystal-clear data. It's no wonder that some of the biggest breakthroughs in coronal research, from spotting nanoflares to mapping magnetic waves, have come from space-based observatories. So while Earth-bound telescopes still play a role, especially for wide-field observations or rapid response studies, they're like trying to listen to a whisper in a windstorm. To truly unravel the corona's mysteries, we need the unobstructed view only space can provide. Next, we'll zoom out even further and ask, does the sun's corona hold clues about other stars in the universe? Now, let's take a step back and look at the bigger picture. The sun isn't the only star with a mysteriously hot corona. Many other stars in the universe show the same puzzling temperature spike. In fact, astronomers have observed scorching coronae around stars both smaller and larger than our sun, from red dwarfs to massive blue giants. This raises a fascinating question. If the sun's corona defies expectations, could the same heating mechanisms be at work across the cosmos? Think of it like this. If you notice that every campfire in a park has flames cooler than the air above them, you'd start to suspect there's a universal principle at play. Similarly, the fact that so many stars share the sun's coronal heating problem suggests there might be a common explanation. Some stars even have coronae hundreds of times hotter than the sun's, with magnetic activity so intense it dwarfs our solar storms. Here's where things get really interesting. By studying these distant stars, scientists can test whether theories like magnetic reconnection or Alfvén waves hold up under different conditions. For example, a rapidly spinning star with a tangled magnetic field might show extreme versions of the same processes we see on the sun. Or a faint, old star with weak magnetism could reveal which heating mechanisms fade first. It's like having a cosmic laboratory where each star is a unique experiment, but there's a catch. While the sun is close enough for detailed study, other stars are so far away that even our best telescopes see them as mere dots. That makes it hard to spot the fine details of their coronae, like nanoflares or plasma loops. Still, clever techniques like analyzing starlight for traces of superheated iron have given us clues. And upcoming missions like the European Space Agency's Plato telescope aim to study stellar magnetism in unprecedented detail. So, does solving the sun's mystery unlock the secrets of all stars? Maybe not entirely, but it's a crucial piece of the puzzle. Every discovery about our own corona brings us closer to understanding the fiery halos lighting up the universe. Next, we'll explore how the sun's mood swings from violent flares to quiet periods might hold even more clues to this enduring mystery. Now, shifting our focus to the sun's ever-changing behavior, let's explore how its mood swings, from explosive outbursts to serene calm, might hold the key to the corona's heat. During active periods, the sun unleashes solar flares, colossal bursts of energy that can outshine entire galaxies for minutes. These flares are like cosmic fireworks, driven by sudden magnetic reconnection, events that superheat localized patches of the corona to tens of millions of degrees. But here's the twist. While flares are dramatic, they're too sporadic to explain the corona's steady million-degree temperature. Enter the quiet sun, those stretches when our star seems placid with no flares or sunspots. Yet, even then, the corona remains blisteringly hot. This suggests a hidden, continuous heating mechanism, like countless nanoflares or persistent Alfvén waves, quietly churning energy into the corona like a simmering pot versus a boiling explosion. Scientists suspect both modes' active and quiet play roles, but in different proportions. During solar maximum, flares might dominate, while in quieter phases, subtle processes take the lead. To put it in perspective, imagine a campfire again. Flares are like throwing a bucket of gasoline onto the flames, a brief, intense roar. But the quiet sun's heating is more like steadily feeding logs to maintain the heat. Both keep the fire going, but in radically different ways. Recent data from the Solar Dynamics Observatory reveals even during quiet times, the corona crackles with microscale energy releases, hinting that the sun never truly rests. So, what does this duality teach us? It means the corona's heat likely isn't a one-size-fits-all puzzle. Instead, it's a dynamic interplay of mechanisms, each dominating under different solar conditions. Unraveling this balance could finally explain why the corona stays hot, rain or shine. Up next, we'll track how decades of failed and promising theories have shaped our quest for answers and why the mystery endures. Now, let's take a step back and trace the winding path of scientific discovery that has brought us to our current understanding, or lack thereof, of the coronal heating problem. The story begins in the 1940s when astronomers first measured the corona's temperature and were stunned to find it was hundreds of times hotter than the sun's surface. Back then, the leading theory pointed to sound waves generated by turbulent convection below the photosphere. Scientists imagined these waves traveling upward, crashing into the corona like ocean waves on a shore, dissipating their energy as heat. But by the 1970s, observations from early space telescopes revealed a fatal flaw. The waves didn't carry nearly enough energy to explain the corona's extreme temperatures. The next big idea came in the 1980s when researchers turned their attention to the sun's magnetic field. They proposed that tiny, frequent explosions, dubbed nanoflares, might be the hidden heat source. Think of it like popcorn. A single kernel popping won't warm a room, but thousands popping non-stop just might do the trick. For a while, this seemed promising, but there was a catch. Even the most advanced telescopes couldn't spot enough nanoflares to account for the corona's relentless heat. Then came the 21st century, bringing with it a wave of new satellites and supercomputers. The Solar Dynamics Observatory, launched in 2010, gave us unprecedented views of coronal loops and magnetic reconnection in action. Meanwhile, the Parker Solar Probe, diving closer to the sun than any spacecraft before it, detected bizarre switchback waves in the solar wind, clues that Alfvén waves might play a bigger role than anyone suspected. Yet, despite these breakthroughs, the puzzle persists. What's fascinating is how each failed theory has sharpened the questions we ask today. We've ruled out dead ends, narrowed the possibilities, and uncovered layers of complexity no one initially imagined. The corona doesn't just defy simple explanations, it thrives on them. And that's the beauty of this mystery. Every answer reveals new questions, keeping scientists and hopefully you hooked. Next, we'll tackle some common misconceptions about the corona and set the record straight with hard science. Now, let's clear up some of the biggest misunderstandings about the sun's corona, because when it comes to this scorching mystery, myths can spread just as fast as solar flares. One of the most persistent ideas is that the corona is hotter simply because it's farther from the sun's surface, almost like the heat magically increases with distance. But here's the reality: temperature doesn't work that way. If you've ever stood near a campfire, you know the air gets cooler, not hotter, the farther you move from the flames. The same logic should apply to the sun, yet the corona defies it spectacularly. Another common mix-up is blaming the heat on direct exposure to space. Some think the vacuum of space somehow cooks the corona, but that's not how physics operates. Space is cold, bitterly cold, and without an atmosphere to trap heat, the corona should lose energy rapidly, not retain it. So why doesn't it? That's the million-degree question we're still untangling. Then there's the oversimplified idea that the corona is just the outer layer of the sun, implying it's naturally hotter like the crust of a pizza fresh from the oven. But the sun isn't a solid object with layers that bake uniformly. It's a dynamic, churning ball of plasma where magnetic forces, not simple proximity, dictate the heat distribution. Here's the kicker: even the notion that the corona is on fire is misleading. Fire, as we know it, requires oxygen, something the sun's atmosphere utterly lacks. Instead, the corona's heat comes from energy transfer via magnetic fields and plasma waves, not combustion. By busting these myths, we get closer to appreciating the real wonder here. The corona isn't breaking the rules of physics. We just haven't fully uncovered the rules it's playing by, and that's where the science gets thrilling. Up next, we'll look at how cutting-edge missions are testing these theories in ways we once thought impossible. Now, let's turn our gaze to the future, because the next chapter in solving the sun's corona mystery is already being written by groundbreaking missions. Leading the charge is the European Space Agency's Solar Orbiter, a spacecraft designed to get closer to the sun than ever before, armed with instruments that could finally crack the code of coronal heating. What makes Solar Orbiter special? Imagine having a microscope and a thermometer combined, but for the sun. This probe carries high-resolution cameras and sensors capable of measuring the sun's magnetic field and plasma waves with unprecedented precision. It's not just observing the corona, it's dissecting the very forces that might be heating it. But Solar Orbiter isn't alone. NASA upcoming missions like the Polarimeter to unify the corona and heliosphere, or PUNCH, will focus on how the corona accelerates the solar wind, another piece of the puzzle. Meanwhile, the Daniel K. Inouye Solar Telescope on Earth, with its massive mirror, will capture razor-sharp images of the sun's surface, revealing tiny magnetic eruptions that could add up to coronal heating. The real game-changer: these missions work together. Solar Orbiter's data will complement Parker Solar Probe's findings, creating a 3D map of the sun's magnetic environment. Think of it as assembling a cosmic jigsaw puzzle, one where every new piece brings us closer to seeing the full picture, and the stakes are high. If these missions confirm, say, that nanoflares or Alfvén waves are the primary heat source, it wouldn't just solve a decades-old mystery. It'd revolutionize how we predict solar storms, protect satellites, and even harness fusion energy here on Earth. So what's next? As these probes beam back data in the coming years, we're not just watching science unfold. We're witnessing the tools that might finally answer why the sun's corona burns so fiercely against the cold void of space. And that's a story worth staying tuned for. Now, here's something truly exciting: the sun's corona isn't just a cosmic puzzle. It's a natural laboratory for clean energy breakthroughs right here on Earth. The same physics that heats the corona could hold the key to unlocking nuclear fusion, the holy grail of limitless clean power. Think about it. Fusion reactors aim to replicate the sun's core, where hydrogen atoms fuse under extreme heat and pressure, releasing energy. But there's a catch. Containing that superheated plasma here on Earth is like trying to bottle a tiny star, and that's where corona research comes in. The sun's magnetic fields effortlessly trap and control its plasma, something our artificial reactors struggle with. By studying how the corona's magnetic waves and reconnections heat and stabilize plasma, scientists are uncovering tricks to improve fusion confinement. Take Alfvén waves, for example. These ripples in magnetic fields, which might be heating the corona, could inspire new ways to stabilize plasma in reactors like ITER, the massive international fusion project. Similarly, understanding how nanoflares dump energy into the corona could help engineers manage sudden bursts of heat in fusion devices, preventing damaging disruptions. And it's not just theory. Labs are already testing these ideas. Some experimental reactors now use magnetic configurations inspired by coronal loops, while others simulate plasma turbulence observed on the sun. Every insight from the corona brings us closer to a reactor that can sustain fusion longer, and maybe one day power entire cities without a speck of carbon. So, while we gaze at the sun to solve its mysteries, we're also stealing its playbook for a cleaner future. The corona's heat isn't just a scientific curiosity, it's a blueprint for the energy revolution. And that's a connection worth shining a light on. Now, let's turn our attention to something that affects us much closer to home: space weather. The sun's corona doesn't just hold secrets for clean energy. Its behavior directly influences solar storms, which can wreak havoc on our technology-driven world. Picture this: when the sun's magnetic fields twist and snap, they don't just heat the corona. They can also unleash massive bursts of energy, solar flares, and coronal mass ejections. These eruptions send charged particles racing toward Earth at incredible speeds. If they hit our planet's magnetic field just right, they trigger geomagnetic storms. The consequences: satellites can be knocked offline, disrupting GPS communications and even weather forecasting. Power grids aren't safe either. A strong enough storm could induce currents in power lines, causing blackouts that last for hours or even days. Remember the 1989 Quebec blackout? That was caused by a solar storm, leaving millions without power in the middle of winter. Here's where corona research becomes crucial. By understanding how magnetic reconnection and waves heat the corona, scientists can better predict when and where these solar storms will erupt. Satellites like the Solar Dynamics Observatory monitor the sun's activity around the clock, giving us early warnings. But the more we learn about the corona's heating mechanisms, the sharper our forecasts become. Imagine a future where we can predict solar storms as reliably as hurricanes. Power companies could safeguard their grids. Satellite operators could put their systems into safe mode. Even astronauts could take shelter from radiation. That's the power of solving the corona's mysteries. It's not just about science. It's about protecting the technology that keeps our modern world running. So the next time you glance at the sun, remember its fiery crown isn't just a distant wonder. It's a force that shapes life right here on Earth. Now, let's step away from the science for a moment and see how this cosmic puzzle is being brought to life for the next generation. Museums and planetariums around the world are playing a key role in making the sun's corona not just understandable but downright mesmerizing for young minds. Take the giant domes of planetariums, for example. With high-resolution projections, they can simulate the sun's swirling magnetic fields and the corona's shimmering plasma in breathtaking detail. Imagine sitting under a virtual sky where you can watch solar flares erupt or coronal loops twist in real time. These immersive experiences don't just teach, they spark curiosity. Interactive exhibits take it even further. Some museums let visitors touch the sun's layers using augmented reality, peeling back the photosphere to reveal the seething corona beneath. Others use hands-on models to demonstrate magnetic reconnection, showing how tangled fields snap and release energy. It's one thing to read about nanoflares in a textbook, it's another to see their explosive power visualized in a dynamic display. And let's not forget eclipse events. When a total solar eclipse darkens the sky, planetariums and science centers often host viewing parties, equipping visitors with solar filters and telescopes. There's nothing quite like seeing the corona's wispy tendrils with your own eyes, a moment that has inspired countless future astronomers. These efforts matter because they turn abstract theories into tangible wonders. A child who watches a coronal loop dance across a planetarium dome today might be the scientist who solves the heating problem tomorrow. By making the sun's mysteries accessible, museums and planetariums aren't just educating, they're fueling the next wave of cosmic explorers. So if you've ever wondered how to share the thrill of solar physics with a young mind, start with a trip to your local science center. Who knows, you might just ignite a passion that lights up the future of space research. Now, let's pull back the curtain on the teamwork behind solving the sun's hottest mystery. The coronal heating problem isn't just a challenge for astrophysicists, it's a melting pot of expertise where scientists from wildly different fields collide to crack the code. Picture this: plasma physicists bring their deep understanding of how charged particles behave under extreme conditions. They're the ones who can simulate how million-degree gas dances along magnetic field lines. Meanwhile, mathematicians whip up complex equations to model the chaos, turning the sun's fury into elegant numbers on a screen. And astrophysicists, they're the bridge interpreting telescope data and space probe readings to test these theories against the real thing. This collaboration isn't just helpful, it's essential. Take magnetic reconnection, for example. Plasma physicists might recreate tiny versions of it in lab experiments, while mathematicians refine the models predicting how much energy those snapping fields release. Then, solar physicists compare those predictions to actual flare observations from satellites like the Solar Dynamics Observatory. It's like a cosmic detective squad, each member bringing a unique piece of the puzzle. Even computer scientists get in on the action. Supercomputers crunch petabytes of data to simulate the corona's behavior, a task so demanding it pushes tech boundaries. Without these interdisciplinary alliances, we'd be staring at the sun with only half the tools we need. The beauty here: breakthroughs often come from the edges where these fields overlap. A mathematician's formula might inspire a new telescope experiment, or a plasma lab's unexpected result could rewrite how we model solar wind. That's the power of collaboration, turning isolated guesses into collective aha moments. So next time you see a stunning coronal loop image, remember, it's not just one type of scientist behind that discovery. It's a symphony of minds, each playing their part to unravel the sun's sizzling secrets. Now let's turn our attention to the lingering puzzles that keep scientists up at night. Despite all the progress, the sun's corona still holds onto some stubborn secrets. One of the biggest head-scratchers: why certain patches of the corona are dramatically hotter than others. You'd think with all that magnetic activity and plasma turbulence, the heat would spread evenly, but no. Some regions blaze at 3 million degrees while nearby areas are relatively cooler. It's like having a campfire where one log is white hot and the one right next to it is barely warm. Then there's the mystery of the sun's poles. Thanks to missions like the Parker Solar Probe, we're getting our first close-up looks at these regions, and they're not behaving as expected. The magnetic fields there twist in ways current models can't fully explain, suggesting there's a whole new layer of physics we haven't cracked yet. And let's not forget about nanoflares. While we've spotted plenty of these tiny explosions, we still don't know if there are enough of them to account for all the corona's heat. Are they the main players or just background noise? It's like trying to measure how many matches it takes to boil a pot of water, except the matches are invisible and the pot is the size of a star. Even Alfvén waves, those energy-carrying ripples in the magnetic field, have their own unknowns. How exactly do they dump their energy into the corona? Do they crash like ocean waves or fizzle out quietly? Every answer seems to lead to two new questions. The takeaway: for every mystery we solve about the sun, another one pops up. But that's what makes science thrilling. These unsolved questions aren't roadblocks, they're invitations to dig deeper, to build better telescopes, and to send more daring probes. After all, the biggest discoveries often start with the humblest admission: we don't know yet, and with the sun, there's plenty we're still figuring out. Up next, we'll explore how you can join the hunt for answers, even from your backyard. Now, here's something exciting. You don't need a billion-dollar spacecraft to catch a glimpse of the sun's mysterious corona. With the right tools and a bit of know-how, you can witness this blazing halo yourself. The easiest way: a total solar eclipse. When the moon perfectly covers the sun, the corona bursts into view like a fiery crown. But remember, never look directly at the sun without proper protection, even during an eclipse. Regular sunglasses won't cut it. you'll need eclipse glasses certified to meet safety standards. If you can't wait for the next eclipse, specialized solar filters are your best friend. These fit over telescopes or binoculars, blocking out harmful light while revealing the sun's outer atmosphere. Look for filters labeled white light for a clear view of the corona's structure. For an even deeper dive, hydrogen alpha filters let you see the chromosphere's spiky features and solar prominences, those fiery loops dancing at the sun's edge. No fancy equipment, no problem. A simple pinhole projector can project the sun's image onto a surface, letting you safely observe eclipses or sunspots. Just poke a tiny hole in a piece of cardboard, hold it up to the sun, and let the light shine through onto another sheet. It's low-tech but surprisingly effective. And here's a pro tip: keep an eye on space agency websites for real-time solar images. Missions like the Solar Dynamics Observatory stream stunning high-res shots of the corona, so you can explore the sun's secrets from your couch. Whether you're using a telescope or a cardboard box, the key is curiosity and a solid respect for safety. After all, the sun's beauty is best enjoyed with your eyes intact. Up next, we'll see how ancient cultures interpreted this celestial marvel, blending science with stories from the past. Now, let's step back in time and see how ancient civilizations made sense of the sun's dazzling corona. Long before telescopes or satellites, people looked up at the sky during eclipses and saw something extraordinary, a glowing ring of light around the darkened sun. To them, it wasn't just a scientific puzzle, it was a divine sign. Take the Maya, for example. They worshipped the sun as a god named Kinish Ahau, often depicted with fiery rays or a radiant crown strikingly similar to the corona we know today. Eclipses were seen as moments when the sun god was battling dark forces, and the corona's appearance was both awe-inspiring and ominous. They even built observatories to track solar events, blending astronomy with spirituality. Over in ancient China, the corona was thought to be a celestial dragon devouring the sun. Emperors would order drums to be beaten and arrows shot into the sky to scare the dragon away, believing these rituals could restore daylight. Meanwhile, Norse myths describe the sun as a chariot chased by wolves, with the corona's glow symbolizing its fleeting escape. Fast forward to modern times, and the corona still captivates not just scientists but artists too. Painters like Howard Russell Butler captured eclipses with breathtaking detail, while photographers use advanced filters to turn the sun's halo into swirling abstract art. Even filmmakers get in on the action, using the corona's eerie beauty to symbolize everything from cosmic power to apocalyptic doom. What's fascinating is how these interpretations, ancient and modern, all circle back to the same awe. Whether seen as a god's crown or a muse's inspiration, the corona reminds us that some mysteries transcend time. Next up, we'll look at how today's scientists are teaming up across disciplines to crack the code of the sun's searing outer layer. Now, as we wrap up this journey through the sun's scorching secrets, let's take a moment to piece together what we've uncovered. The corona's blistering heat, millions of degrees hotter than the sun's surface, remains one of space's most tantalizing puzzles. But thanks to tireless collaboration among astrophysicists, plasma researchers, and engineers, we've edged closer to answers. Magnetic reconnection, Alfvén Waves Nanoflares. Each theory offers a piece of the puzzle, yet the full picture still shimmers just out of reach. What's truly inspiring is how this mystery unites us. From ancient skywatchers to modern-day scientists staring at supercomputer simulations, humanity's quest to understand the corona spans cultures and centuries. Missions like the Parker Solar Probe and Solar Orbiter are rewriting textbooks, while groundbreaking telescopes capture the sun's drama in exquisite detail. And let's not forget, every eclipse chaser with a camera or backyard observer with a solar filter adds to this collective curiosity. So what's next? The story isn't over. With upcoming missions poised to dive even deeper into solar physics, who knows what revelations await? Maybe you'll be the one to spot the next clue in a coronal loop or a magnetic wave. Until then, keep looking up and stay tuned. After all, the sun's next big mystery might be just a solar flare away. If you've enjoyed unraveling this cosmic enigma with us, don't forget to hit that like button and subscribe. Ring the bell so you never miss an update as we continue exploring the universe's greatest puzzles. Thanks for joining the adventure, and remember, every discovery starts with a spark of curiosity. See you in the next video.